Exploring the landscape of reasoning in large language models. In recent years, the field of artificial intelligence (AI) has witnessed substantial advancements, particularly with the development and deployment of large language models (LLMs). These models, such as OpenAI's GPT series and Google's BERT, have revolutionized natural language processing by performing tasks ranging from simple text generation to complex reasoning. One of the most intriguing capabilities of LLMs is their ability to engage in reasoning, a cognitive process that involves logical thinking and decision-making. This blog post delves into the intricacies of reasoning within LLMs, exploring its methodologies, applications, challenges, and future prospects. Understanding reasoning in LLMs. Reasoning is fundamentally about deducing or inferring conclusions from premises or known information. It encompasses several forms. Deductive reasoning draws specific conclusions from general premises. Inductive reasoning infers general patterns from specific data. And abductive reasoning suggests the most plausible explanations based on incomplete information. 7. In the context of LLMs, reasoning involves leveraging vast amounts of encoded knowledge to solve problems or answer questions systematically. Types of reasoning in LLMs. 1. Deductive reasoning. This form relies on predefined rules to derive a conclusion. For example, if all birds can fly and a sparrow is a bird, then it follows deductively that a sparrow can fly. 7. 2. Inductive reasoning. Unlike deductive reasoning, inductive reasoning involves predicting generalizations based on specific instances. For instance, seeing multiple examples of birds flying might lead one to conclude that all birds fly, a conclusion that might not always be correct, but often holds true. 8. 3. Abductive reasoning. This is about finding the best explanation for observed events. It's frequently used in diagnostic scenarios like medical assessments where symptoms are observed and potential causes are hypothesized. 7. Techniques for enhancing reasoning. LLMs employ various techniques to enhance their reasoning capabilities. Chain, a thought prompting. This involves guiding LLMs through a structured thought process by breaking down complex problems into simpler sub-problems. 1. By prompting models step by step, they can arrive at solutions more logically. Few-shot and zero-shot learning. These techniques enable models to perform tasks with little to no task-specific training data by leveraging prior learned knowledge. 1. Reinforcement learning. Recently introduced models like OpenAI's O1 use reinforcement learning to improve reasoning by simulating decision-making processes akin to human problem-solving strategies. The model learns from feedback, thereby enhancing its performance over time. 2. Applications of LLM reasoning. The ability of LLMs to reason has broad implications across various domains. Scientific research. In scientific disciplines such as physics and biology, LLMs are employed to reason through complex datasets and simulations. Models like OpenAI's O1 have shown proficiency in solving problems typically tackled by experts in these fields. 2. Their capacity to handle abstract concepts makes them valuable tools for hypothesis generation and testing. Healthcare. In healthcare, LLMs assist in diagnosing diseases by interpreting symptoms and suggesting potential diseases through abductive reasoning. They can analyze patient histories alongside current symptoms to provide diagnostic recommendations that support clinicians' decisions. 8. Legal analysis. LLMs are increasingly being used for legal research and analysis. They can review legal documents and identify relevant precedents or statutes that apply to new cases. By understanding legal language nuances and applying logical rules, they assist lawyers in forming compelling arguments. 7. Creative industries. Beyond analytical tasks, LLMs influence creative fields by generating new content ideas or even composing music and art based on learned styles. Their ability to mimic human-like creativity stems partly from reasoning processes that synthesize diverse inputs into coherent outputs. 6. Challenges in LLM reasoning. Despite these advancements, several challenges persist in optimizing LLM reasoning abilities. Logical consistency. Ensuring logical consistency remains challenging because models sometimes produce contradictory statements or illogical conclusions due to inherent biases or limitations in their training datasets. 4. Efforts continue towards improving model architectures and fine-tuning methods that minimize such inconsistencies. Handling ambiguity. Natural language often contains ambiguities that complicate reasoning tasks. While humans use context effectively to resolve ambiguities, teaching machines this skill is less straightforward. Current models struggle with nuanced interpretations unless explicitly trained on similar examples. 5. Ethical considerations. As with any powerful technology, ethical concerns arise regarding misuse or unintended consequences when deploying LLMs capable of advanced reasoning. Ensuring transparency in decision-making processes becomes crucial, especially when these systems are involved in critical areas like law enforcement or healthcare diagnostics. 5. Future prospects. The future promises exciting developments as researchers aim for more robust solutions. Enhanced multimodal capabilities. Integrating text-based reasoning with other modalities such as visual data could lead to richer insights, especially especially useful for applications requiring comprehensive situational awareness such as autonomous vehicles or surveillance systems. 3. Improved interpretability. Ongoing research focuses on making AI models more interpretable so users understand how decisions were made, a critical feature for trustworthiness, especially in sensitive applications involving high-stakes decisions like finance or security assessments. 8. Expanded collaborative efforts. Collaboration between AI systems could drive significant advancements where one system verifies another's output. Similar mechanisms already exist informally among humans working collaboratively across disciplines, but formalizing them within AI networks offers potential efficiency gains. 3. Conclusion. Reasoning represents one frontier where AI continues expanding its boundaries beyond simple automation towards cognitive emulation reminiscent of human intellect, albeit limited currently by constraints inherent within existing technologies themselves rather than conceptual possibilities alone. If properly harnessed responsibly moving forward, carefully balancing innovation against attendant risks, mindful societal impact, ultimately shaping our collective future, informed, guided, powered, increasingly intelligent systems built around us today, tomorrow alike, forevermore reshaping, redefining humanity itself anew, each passing moment together, always remembering why we started, embarking journey, first place, striving, better, brighter world, everyone, everywhere, every time. Once again, finally closing thoughts. Thanks joining exploration today, looking forward seeing next time. Until then, take care, stay safe, goodbye now. Sources. 1. Source: LLM reasoning. 2. Source: learning to reason with LLMs. 3. Source: at Fortes of awesome LLM reasoning. 4. Source: logical consistency of large language models in fact. Teching.pdf. 5. Source: Right vs. Right, can LLMs make tough choices.pdf. 6. Source: abstract reasoning with large language models. 7. Source: understanding reasoning in large language models. 8. Source: understanding the current state of reasoning with LLMs.